Welcome back, everyone. In this video, I'll be going over the limits at infinity lecture. Now, to start, what is a limit at infinity? It's not something we've dealt with before. We dealt with infinite limits before. We saw limits that we could get infinity or negative infinity as their answer. But a limit at infinity can be described as taking the limit of a function as x goes to infinity or negative infinity. Specifically, when we're talking about limits at infinity, where in our notation we have limit as x goes to infinity of f of x or limit as x goes to negative infinity of f of x. This is what indicates a limit at infinity. Whatever the number that comes out when you do the limit has no bearing on whether you would say we're doing a limit at infinity. Right, so that's going to be some vocabulary that could be a little confusing when you interact limits at infinity with infinite limits. So just keep in mind, limits at infinity means the x value. Think about x being described as the word at. X and at are synonymous, and when we say limits at infinity, we're talking about x going to infinity or negative infinity. Now, one thing I want to repeat throughout the lecture, because it's probably the most important idea at this point about limits at infinity, is that when you get a number, a finite number, so not infinity, as the limit at infinity. So let's say this was 2. When we did the limit out somehow, we got 2. We would say y equals 2 is a horizontal asymptote. As long as the number is finite, it's a horizontal asymptote. And because each one of these can give you a number, you can have up to 2 horizontal asymptotes. So we'll see that as we go through the section, but that's one of the main points of emphasis, is knowing if you have a horizontal asymptote or not. Now, this is pretty much what I just said, is that the limits at infinity are only referring to the x value and have nothing to do with the y value. But I want to go ahead and just jump right into looking at limits at infinity of a graph. And we'll talk about a drawback as well, a couple drawbacks rather. But limits at infinity, when we talk about, let's focus on the limit as x goes to infinity portion first. Well, if x is going to infinity, you could imagine that if you were, let's not even worry about the graph at this point, but if you were just walking along the x-axis and you want to go towards infinity, well, the smart thing would, as far as drawing our person or whatever you like to do to think about limits, is that we're walking to the right, because that's when x gets big, but we never reach infinity. The idea with infinity is that no matter how far you walk, how big x gets, you can always add more to it to make it bigger. If I have 9, 9, 9, 9, 9, a bunch of nines, I can keep writing 9 forever. I can always just add 1 and then I'm still closer. I mean, it's still bigger. So I never get to infinity. That's the whole idea with infinity, is that you never get there. So one drawback of limits at infinity is that you can't actually plug in infinity or negative infinity. But it's a very handy way to think about it in your head, is when you're thinking about limit at infinity, specifically as x goes to infinity, or walking to the right forever. We're asking what's happening to the graph as it moves to the right forever. And that's exactly the way I like to think about it, is moving to the right. And with the same idea, when you do the limit as x goes to negative infinity, that's walking all the way to the left forever. The same idea. You never can get there. So, you're not going to be able to plug in negative infinity. But we'll see how to work around that as we go through the section. All right, now with that said, I want to go ahead and just jump into this problem. We have the limit as x goes to negative infinity, and then a couple others that aren't limits at infinity. Let's do the negative infinity one first, just because it's the first one in order. And we want to walk towards negative infinity for x. So we want to keep going to the back forever, to the left. And what we have to do with graphs, especially limits at infinity, is we cannot see infinity and we can't draw infinity. That works for x and y. We've already talked about vertical asymptotes, so we know why we have to make assumptions here. As we move to the left, we have to assume that this flattening out is going to flatten out exactly where it looks like it is. It's flattening out at the x-axis. Oops. So it's flattening out at the x-axis. As we go towards negative infinity, we're going to basically be at the x-axis, which is the y value of 0. We know with limits, we want the y value. That means the limit as x goes to negative infinity is just 0. Now, as we go to the right, of course, I want to actually be on the graph this time. So I'm going to draw the little guy up here. And if I'm going towards x to infinity, going to the right forever, the y value here, it's leveling off again. So we have to assume it's going to stay at this level. It's not going to go back up or turn down. And the y value there is the 2. That's why I indicated the 2 there. All right, now the last two here are just limits that we've been dealing with since the first section. Nothing new here. The limit as x goes to negative 1. Well, as we go towards negative 1 from the left, goes towards positive infinity. As we go towards negative 1 from the right, we go down towards negative infinity. And we know when those are different, it's d and e. And then as we go towards 3, from both the left and the right, it's going towards positive infinity. So this one is positive infinity. All right, so just a clarification on wording, again, is that when you get infinity out, this is what we call an infinite limit. Because infinity is coming out. It has nothing to do with the number coming in. So this 3, it could have been infinity as well. But if what's coming out is infinity or negative infinity, we call this an infinite limit. The first two, I'll intentionally point over here because I'm focused on the x values. I don't really care about the y values when I talk about limits at infinity. Okay, so limits at infinity, x value, infinite limit, y value. Very helpful. Now, one thing also that you may have noticed is that when we walk all the way to the left, when we walk all the way to the right, we can only walk or approach one way. We can't approach x is negative infinity from the left because we're never going to make it to infinity. Just as a little quick drawing here, let's say take my guy here and he's walking and infinity's right here. We know we can't actually draw this because it's never there. But let's say infinity is over here. Well, because we can never actually get there, we can't walk from the left, or sorry, from the right. It's always going to be approaching infinity from the left. So when you're talking about limits at infinity as well, it's automatically a one-sided limit, but that's okay because that's all we can do. But that could be an important thing that comes across when you have certain problems. Limits at infinity are automatically one-sided limits. All right, so something important that I wanted to add in, I pretty much said this already. If the value of a limit at infinity is finite, now both of these up here are finite, 0 and 2, the limits at infinity are finite, then it is a horizontal asymptote. So to relate this, what I would say here is for this graph, I have 2 horizontal asymptotes because these are 2 different numbers. If they were the same number, I would just consolidate it together and say it's 1. But this graph here has 2 horizontal asymptotes. Y equals 0 because that was one of my infinite limits, or sorry, limits at infinity. And then y equals 2 as well are both horizontal asymptotes because we got those values for limits at infinity. So just to relate this to our graph above, what I'm saying here is y equals 0 and y equals 2 are horizontal asymptotes. I'll abbreviate it HA like I do vertical asymptotes VA, are both horizontal asymptotes for the graph above. And if the value of a limit at infinity is infinite, we don't have that example here. And the main reason we don't care too much about if a limit at infinity is infinite is because it's not a horizontal asymptote. Some places will write infinity or negative infinity depending on which way it goes. But for us, we're just going to write D and E. So just as a very quick drawing here, you can imagine if we're going to the right forever, maybe you know what a parabola looks like. So actually I can just draw the right half of a parabola. It's going to go up forever. The limit as x goes to infinity of f of x, don't worry about the actual equation, it's just x squared, but not important, is infinity. Some books might write that. Some resources might write that. Some will say D and E, just because it's not finite. Typically, we only care if a limit is infinite, if it's occurring at a finite number, because that means we have a vertical asymptote. When you're going all the way to the left, all the way to the right, you don't say there's a vertical asymptote because you never actually have this stopping point. So just something to keep in mind. I will use the common thing, which is to write D and E. All right, but once again, this is only for limits at infinity. If a limit at infinity is infinite, we will write D and E. If a limit is infinite at a finite number, like 3, like we had here, we'll still write infinity. All right, so this next little bit, I want to talk about important limits at infinity and where they actually come from. You pretty much need to understand these because we can never actually plug in infinity. And these limits are what we're going to use to know how to evaluate limits at infinity. Now, at this point, we don't have limits at infinity for a bunch of different functions. So you'll notice I have x to the n, I have 1 over x to the n, I have just a number like f of x equals 3. I have exponential functions as the next pair. Sine or cosine, we could actually do every trig function, but really sine or cosine explains them all. And then very special arctan. So this what I'm writing here for arctan will not apply for all inverse trig functions. All right, but what I want to go ahead and do is explain how these come up and what they mean. And you'll notice on some of them, like when we have D and E here for x to the n, you'll notice I wrote D and E because that's what we're going to use because it's infinite. The output is going to be infinite, but I specified whether it's infinity or negative infinity where it'll be applicable. But what I'll go ahead and do is open up Desmos and show you how these work for a few examples. So for x to the n, I should not have that hidden. N is just representing any positive integer. And what this is saying is that when you have a positive integer on x, you always get an infinite limit if we go to the left or if we go to the right. Y equals, let's just do x raised to the 4th power first. I'm going to go ahead and make it bigger, but I'll show the chart again. So you'll notice that if I scroll out, it's just going to keep going up. It goes up really steep, but it's going to keep going to the right no matter what. So what this is saying is that the limit as x goes to infinity, as we go to the right, the y value is infinity. But as we go towards negative infinity, as we go to the left, it's also going to approach positive infinity. And when we have x to the n, as we go towards infinity, as it goes to the right, it's always infinity. It doesn't matter what n is. Now, when you're going toward negative infinity, it does matter. If n is even, which we had for that example of 4, then it goes towards positive infinity. If n is odd, like 3, then it'll go towards negative infinity as we go to the left. And I'll just go ahead and graph y equals x cubed right on top of it so you can see that happening. For x cubed, as we go to the right, it goes towards positive infinity, but as we go towards the left, it goes down to negative infinity. Did not want to highlight that. So that's just something to keep in mind. You know, I don't necessarily want to tell you these as far as memorizing completely, but if you need to replicate them, keep in mind you have a calculator, just use a base example. All right, what about 1 over x to the n? Well, this is probably the best one there is besides also the number one below. It's because when you have 1 over a power of x, then it's always 0 as you go to the left or the right. So this can be any power of x, by the way, any positive whole number. It doesn't matter if it's even or odd. So 1 over x looks like this. Go ahead and scroll in a little bit. But what this is saying is as we go to the left, the y value goes to 0. As we go to the right, the y value goes to 0. As we go to the right, we can see the y value is definitely going to 0. If you scroll out, it just keeps going to 0. I can keep going to the right. It's going to keep getting closer and closer to 0. And now if I go to the left, the same thing's happening. Look at the y value. it's pretty much on the x-axis. It's the y value is barely negative. It's close to 0, and it's just going to keep getting closer. Okay, and once again, it doesn't matter if you have an odd number, which that is, or an even one. So I could do 1 over x squared. The only thing that's different is around the origin where the asymptote is. X equals 0 makes the denominator 0, so you do have a vertical asymptote there. It's just going to look different there. But as you go to the right, as you go to the left, it's still going to go towards 0. All right, the next one is maybe the easiest to explain, because if you just have y equals a number, I just have 3 here. I'll scroll in so we can see this is just a horizontal line of 3. As we go to the left or to the right, the y value is always 3. It's just going to stay 3 forever. That means as we go to the left or the right, you're still going to be stuck on 3. So whatever your number is, that's it. All right, what about exponential functions? Well, when the base is bigger than 1, y equal, I'll use e to the x because that's the most common one. That's your increasing one. As you go towards the right, what's happening is it's just going to keep going up forever. So you get d and e for us, but it's always positive infinity. As we go towards the right, it's always positive infinity. Now, as you go towards the left, it's just going to stay barely above the x-axis, eventually get so close to it that we basically call it 0. And as we go towards the left, you'll get 0. Now, if the base is between 0 and 1, that's the exponential graph that's decreasing. And that's why it's going to be pretty much the opposite. I'm going to change this to 1/2. Oops. Just to be between 0 and 1. Why is it giving me an error? Subscripts can, oh, it thinks I want a subscript there. Y equals 1/2 to the x. You can see it's just pretty much the opposite. As we go to the left, it goes to positive infinity, which we'll call d and e. And as we go to the right, it goes to 0. All right, what about sine or cosine? I'm just going to do 1 because we know the graphs of these look the same. We should know that the graphs of sine and cosine are these wavy patterns. As we go to the right or to the left, what's happening is it's never coming to a point. It's always going up or down, up or down. No, if I keep going to the right forever, it's just going to keep going up and down, which means it's not coming to a definite y value. It's oscillating. So that's why it's d and e. Same thing if we go to the left. It's the same graph. It's periodic, so it's going to have the same exact shape no matter what. And as we go towards negative infinity, same idea. It's oscillating. It's going between 1 and -1, so it's d and e as well. This actually is true for every trig function, but the other 4 trig functions have a ton of vertical asymptotes. If you remember, like tangent of x, it's still d and e. All 6 trig functions are, but for the most part, we only use sine or cosine. Now, arctan is very special because it's one of the few graphs that has 2 vertical asymptotes, 2 horizontal asymptotes, and the y value of them is special. Okay, so as we go to the left, the value of arctan becomes like -π/2. Remember, -π/2, if you type that in your calculator, or just, I can show you real quick, it's about -1.57. And if you look at the y value here as we go to the left, it looks like it's going towards -1.5 something. And then eventually, the farther left you go, the closer it'll get to -1.57. So as we go to the left here, arctan goes towards -π/2, but you do need to use -π/2, not -1.57. As we go to the right, it just does the exact opposite and goes towards 1.57 or π/2. And so arctan has 2 horizontal asymptotes because these are 2 finite numbers that are different. 1 over x to the n had 1. This one has 1. This one has 1. This one has 1 because they all have finite numbers. 0 is fine. But arctan has 2. Now, if you want to remember why arctan, this value is π/2, if you graph y equals tan of x, let me go ahead and make a slight adjustment here. For Desmos, you can do a lot with the axes. I'm going to do negative pi for x to pi just to look at tangent. And I'm going to do a step size of pi over 2. So what that's going to do is it's going to label my x-axis pi over 2 perfectly. The graph of tangent here, as we go towards pi over 2, we get a vertical asymptote. And as we go towards negative pi over 2, we also get a vertical asymptote. The one thing you should, in general, remember about graphs is when you graph their inverse, x and y switch. So vertical asymptotes on the regular function at pi over 2 become horizontal asymptotes on the inverse function. So that's how I know that this horizontal asymptote goes towards pi over 2. It's because the graph of tangent has a vertical asymptote at pi over 2. Okay, so that's really where the pi over 2 is coming from. But what I'll stop here. What we'll do in the next video is actually pretty much the rest of the section. We're going to focus on using these properties to evaluate limits at infinity. And one thing I'll go ahead and mention is that pretty much any function that isn't involved here, natural log, things like that, we can't do yet with limits at infinity. So keep that in mind as we go forward, why you might not see natural log or other functions. This is pretty much all we're capable of dealing with.